Hello. Today, I, Vasu Mishra, and my friend Ankit Sharma are going to present on the topic constant velocity joints for front axle shafts. Historically, universal joints have been known by many different names, such as Hooke's joint after Robert Hooke and Cardan's joint after Geronimo Cardan. At its core, universal joints solved a huge problem for automobile engineering. Their primary purpose is to transmit power between two shafts that are intersecting but not parallel. The universal joint consists of three primary members: the driving yoke, the driven yoke, and the spider. When the two shafts are parallel to each other, the ends connected to the driving yoke, this one, and the ends connected to the driven yoke, this one, on the spider, rotate in the same plane. However, when the two shafts are at an angle, the ends connected to the driving yoke and the ends connected to the driven yoke rotate in two planes that are inclined to each other. This inclination introduces an angular variation in the ratio of output and input velocity. Thus, the output velocity is not constant even if the input velocity is constant, which means that the angle at which the two shafts are inclined plays a factor in the output rotation. To overcome this, constant velocity joints were introduced. The very basic constant velocity joint was a double Hooke's joint, which was simply coupling two universal joints in order to cancel out the angular variations. Furthermore, Bendix joints, Zeppa joints, and tripod joints were also introduced, which were further enhancement of the basic universal joint.
So now we'll see the omega transmissions that occur in a Cardano joint. As we can see on our left, we have a rough diagram that represents the cross of a Cardano joint. X1 and X2 represents the arms of the Cardano joint. As we can see, X1 can easily be represented using polar coordinates as cos gamma 1, comma sine gamma 1, comma 0. Now, if we were to assume that x2 cap was in the same plane, we would have its coordinates something like minus sine gamma 2 cos gamma 2 comma 0. However, since we know that these planes are at an oblique angle, assume that they are at an angle beta, we use a clever technique of using the rotational matrix to get the actual coordinates of x2. We have written the rotational matrix according to the rotation, and finally we get the coordinates of x2 cap as the one that's given in at the bottom of a page in the right side. The next trick that we use, that is a very important part, is the fact that x1 and x2 represent the arms of the cross. That is, x1 cap and x2 cap are always perpendicular to each other, which gives us that x1 and the x1 dot and x2 dot would be 0, which gives us the relation that tan gamma 1 is equal to cos theta into tan gamma 2. Now we already know that omega 1 and omega 2 are the time derivatives of gamma 1 and gamma 2 respectively. Differentiating on both sides and simplifying, we get the relation between omega 1 and omega 2. This relation, as we can see, is a complex trigonometric relation as said by my friend Vasu. Now we need to understand the problem. The first universal joint, which is called the Cardano joint, failed to provide a constant angular velocity output. This was first recognized by Robert Hooke, who gave a very clever solution, which consisted of two Cardano joints that were offset or out of phase by 90 degrees. This cancelled out the velocity variations. Due to oscillating angular velocity and the fact that these joints might be used in high angular velocity situations, for example in cars, the phenomena of fatigue comes into picture and plays a very important role. Therefore, failure occurs much easily in Cardano joints than other type of joints. The fact that these joints can enhance torque transmission than the amount that is applied or we need leaves a lot of space for a chance of overloading. So the front axle requirements are as follows. For the outer CV joint, it must be a constant velocity joint, obviously. And another important point is that they should have ample angular freedom that is required during turning. The most common type of CV joint fulfilling all these criteria is the Zeppa joint. For the inner CV joint, it must be a constant velocity joint, and it should also allow for some angular freedom. Another important point is that it should allow for minute length changes that occur during road bumps and turns. The most common type of CV joint that fulfills all this criteria is the tripod joint. As we can see, this is a simple layout of a front axle shaft, which shows us the outer CV joint, which is a Zeppa joint, and the inner CV joint, which is a tripod joint.
Let's now discuss some of the CV joints in further detail. A typical CVJ drive shaft in a car these days consists of a Zeppa joint and a tripod joint. Towards the wheel, we have Zeppa joints because they can allow for higher angles. Zeppa joint can be considered as an enhancement of a Bendix joint, wherein a Bendix joint you have a spigot and slotted swivel. Zeppa joints contain outer race, inner race, typically 6 balls and a cage. These balls are allowed to slide along these grooves made on the outer race. This relative motion only comes into play when the two shafts are at an angle. These joints can perform well at high angles and high frequency of change of angles, and can perform well or at angles up to 48 degrees. The inner CV joint is a tripod joint. As can be seen in the schematic diagram, this is the input shaft and this is the output shaft. The input shaft has three arms attached to it, at the end of which there are spherical rollers, which are allowed to slide in grooves made on the output shaft. The movement of these spherical rollers are relative to the output shaft. The angular articulation allowed by tripod joints is only 26 degrees compared to the 48 degrees of Zeppa joints. However, their simple structure allows for efficiency and reduces the cost by a great degree.
Now we'll locate the CV joint, both of the CV joints in an actual car, and we have recorded a video. So this is the Zeppa joint that is the outer CV joint connected directly to the wheel. It allows for greater angular movement and uh, prevents axial movement. This is the tripod joint. Allows for lesser angular movement, gives us greater axial movement. This is a constant lattice joint as well. So finally, we have come up with a potential hybrid of a Zeppa and a tripod joint. As we can see on the right, we have sketched a rough diagram. The outer casing looks very similar to a tripod joint due to the fact that we would be using a spider that is similar to a tripod joint. However, instead of cylindrical bearings that mounted on needle bearing, instead of uh, cylindrical bearings mounted on needle bearings, we would directly use ball bearings. The advantage of this is that unlike the Zeppa joint, axial freedom would be allowed. This would allow for small length changes. Also, unlike the tripod joint, which has curved cylinders on needle bearings, this design has simple ball bearings, which allow for greater angular freedom. That comes into picture due to the ball bearing, and also has lesser moving parts. So this is our presentation. Thank you.
Thank you.